Hi guys, in this video we'll look at various examples of Sn2 reactions. The first will be alkylation of oxygen. And what we'll see is that for Sn2 we must first make the oxygen an anion, because remember we need a strong nucleophile for an Sn2 reaction. Let's look at alkylation of carboxylic acids. Okay, this carboxylic acid, we have a neutral oxygen. That's a poor nucleophile, a weak nucleophile. It's not going to be able to do an Sn2 reaction as is. Let's draw in a bond here. Okay. We can convert the carboxylic acid to the anion, the carboxylate anion, the oxygen anion, by reaction with a base. Bases remove H's. We can use, most common base is hydroxide. What about sodium hydroxide? These electrons take the H, these electrons stay behind. We get the carboxylate anion plus water, and the sodium spectator ion can sit with that. But now we have converted the neutral OH group, the neutral carboxylic acid, to the anion, the carboxylate. And now this is a good nucleophile. It's an anion. Yes, it is delocalized, but it is still a sufficiently strong nucleophile. Now if we come in with a substrate with a leaving group, which can be an electrophile, the thing the nucleophile will react with, I will typically call it the substrate with the leaving group. Now we can do our Sn2 mechanism, and these electrons come in here and backside attack and kick off the leaving group. And now the oxygen is bonded to that carbon. We just made that bond. I like to highlight the bonds we make sometimes with a little ziggly line. And so instead of a bromine being bonded to that ethyl group, now that oxygen is bonded there. And we have alkylated. We've put an alkyl group on the oxygen. And so we've done an alkylation. We've also can note that we have converted the carboxylic acid to an ester when you put the R group on. So this is a way to make esters by alkylation of the oxygen. In this case, an ethyl ester using ethyl bromide, or a more IUPAC name, bromoethane. Alright, so this is a standard Sn2 reaction, but we first had to generate the stronger nucleophile. Alright. Now, this reaction sequence may often be shown sort of, I showed two separate steps. We could have showed, I'm just going to do this instead of redrawing the product. A lot of times you'll say maybe 1 sodium hydroxide and then 2 ethyl bromide. If you remember way back during test 1 when we first looked at lime reactions, I showed you that some lime reactions can have multiple steps. Well, this would be a multiple step lime reaction where we don't show any intermediate. The intermediate would be here after step 1. Would be the anion, but I'm not showing that. Then in a separate step, okay, We then come in, we add the ethyl bromide, and that's when the Sn2 reaction would take place. These two are not combined. If the 1 and 2 was not there, all this would be added together. But the 1 means one step is conducted, then usually in the same exact flask, same exact round bottom, we then come in with a second set of reagents, in this case just one reagent. Okay. So that was an example of alkylation of oxygen, carboxylic acid. What about an alcohol? Can we alkylate an alcohol? Well, again, neutral nucleophile. A neutral oxygen is not a good nucleophile. We need to convert this to the anion. Can sodium hydroxide do it? The answer is no, it cannot. Now here I'm just showing this ONA, of course that's ionic. Just like if we showed NaCl, we know that's really Na plus and Cl minus. This here is really Na plus and O minus. If you like to get rid of the sodium and put the lone pairs here and say there's your oxygen anion. Well, sodium hydroxide will not do this. Let's think about pKa. pKa of an alcohol is like water, it's about 16. We would make the anion plus water, its pKa is also 16. Which side is favored? Well, neither. It's actually a 50-50. But in practice, 50-50 doesn't work for various reasons I'm not going to get into. We've mentioned before in class, you need about a difference of 2 to 3 pKa or log units for it to be a complete reaction. This is not a complete reaction. It will not work, not good. Now up top, this had a pKa, carboxylic acid, of about 4, and water's about 16. Which side's favored? Well, 16, the weaker acid, and it's favored substantially. It's favored by 10 to the 12. That's like 100 billion. Okay? But it's not favored with the regular alcohol. Thus, you cannot use hydroxide to convert an alcohol to the alkoxide. What can you use? You can use sodium metal. This is not Na+, this is just sodium metal. Oxidation state of 0. It will convert the alcohol to the sodium alkoxide. The fate of the H here is hydrogen gas. Now this is not a acid-base reaction. It is a redox reaction. But it generates the same product that we're looking for that would come from an acid-base reaction. Nothing takes the H. It's redox. We're not going to show a mechanism for this. Redox mechanisms are harder to show. They tend to be radical reactions. All right? Now you can balance this if you want. You need 2 alcohols. Okay? You want to balance it? 2 of these react with 2 of these, and to give 2 of those, and only 1 of those. So now on this side we have 2 sodiums, that side we have 2 sodiums. Okay? But it doesn't matter. You take an alcohol, you add sodium, you'll get the sodium alkoxide plus hydrogen gas. Bubbles of hydrogen will come out. All right? We may demonstrate that reaction in lab. You may have seen that demonstrated in Gen Chem lab. I know we used to do that. Okay, sodium metal. So that will work. All right. Now another way to generate the alkoxide is to use sodium hydride. Now this is a standard acid-base reaction. Now what's the charge of the H here? Well, it's Na plus and H minus. Hydrogen has a lone pair. I don't know that we've seen sodium hydride before. We've talked about hydride shifts, where the H and the 2 electrons shift over during carbocation rearrangements. You don't often see sodium hydride. You may not have seen it before, but it is possible. Here we can do a standard acid-base reaction. Let's draw the H bond out. These electrons take the H, these stay behind to become the third lone pair. Make the oxygen anion, the sodium cation can sit with that, and we generate what right here? Hydrogen gas. Similar as above, but again, above was a redox reaction. This is more of a standard acid-base mechanism. Two different ways, though, to generate alkoxides. So, take an alcohol, react it with sodium metal. We generate the alkoxide here. Strong nucleophile. Now we can come in with a substrate with a leaving group and bam, backside attack, kick off the chlorine leaving group, and now the oxygen is bonded to the CH2 and that's bonded to a phenyl, and we just made that bond right there. And in this case, the alcohol was converted to an ether, as we set up here. All right, well, we called it, this sequence here, again, it's a two-step sequence, a 1 and 2, is called a Williamson ether synthesis. Williamson is a chemist, I believe English chemist from back in the 1800s, who said, hey, I can convert alcohols to ethers. I can make ethers from alcohols. I first have to react my alcohol with something to generate a basic form of it. Eventually became known as the alkoxide. Then when I throw in something with a leaving group, I get this chemistry taking place, and I can maybe distill or recrystallize an ether product. And this is the most common way to make ethers. Again, from an alcohol. Now you can also do this with phenols. But with phenols, you can use hydroxide. All right? Hydroxide takes the H, we make water, and the sodium phenoxide, 10, 16, which side's favored? Well, the weaker acid by 10 to the 6th. That is enough for this to be favored, and it will work. Hydroxide can be used to generate the anion of a phenol, but it cannot be used to generate the anion of a regular alcohol. Of course, the phenoxide is much more stable because it's resonance stabilized anion. So a two-step sequence. Take phenol, react it with sodium hydroxide, make the sodium phenoxide, then we come in here with something like methyl iodide. Again, let's sort of get rid of that spectator ion if you want. Minus. Of course, I don't like how that's really drawn. The iodine's really bonded to the carbon, right? These electrons attack the carbon. Kick that off. The oxygen is now bonded to the methyl group. Methyl iodide is pretty darn reactive. If you remember, iodine is the best of the halogen leaving groups. Also, the carbon has no sterics. These H's are real small, and so this oxygen anion can get in there pretty easily. Methyl iodide tends to be toxic because it's so reactive. It'll react with the nucleophiles in your body. It's a potent methylating reagent. Okay? We can call it an alkylating agent. That's a general term. Methylating reagent or agent would be a more specific term for the 1-carbon alkyl group. We converted the phenol to the ether, phenyl methyl ether. Okay, we can also make rings this way. Rings with an oxygen in the ring. If we treat this compound here with sodium metal, we get this product and these two byproducts. Well, what does sodium do to an alcohol? It converts it to the alkoxide plus hydrogen gas. Now this can come right over here and bam, kick off the leaving group. And that's going to give that product there. Oxygen, carbon, 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 carbon. So 1, 2, 3, 4 carbons and oxygen all ring the oxygen. And so we made the bond either side. We can say we made here 4 carbons. The oxygen came back around and attacked that 4th carbon. That's what happened here. And so we can make this ring by an intramolecular Sn2 reaction. Of course, the sodium cation is here, and then the bromide leaving group, and we can show those together. And so we can say that sodium bromide has also been formed in this reaction. Isn't it great to be able to see how sodium bromide and hydrogen are formed here, and we don't just have to sort of memorize this? Okay, right here is your bromide being formed. Got 3 lone pairs. This arrow puts the 4th lone pair, Br minus. The sodium was formed in this redox reaction. It's sitting here. At this point it becomes a spectator ion. And when that leaves, we have sodium ions and bromide ions. By the way, back over here with the redox, you can see it's redox because the sodium metal, okay, this is now Na+. The sodium lost an electron. It became a positive. So the sodium was oxidized, and now this is not formally H+, but this is, the H here is considered +1 in terms of a redox count. But now the H is considered, that's elemental hydrogen. The redox would be 0 here, and so it went from +1 to 0. The hydrogen has been reduced. Okay. Now with the Williamson ether synthesis, we need to be able to go backwards. That is, what reaction would you propose to form these ethers? Now we just need to go backwards. We need to go back to what? We need to go back to an alkoxide, okay, right? Or more broadly, an oxygen anion, because it could be a phenoxide. And then we need substrate with leaving group. Those are the 2 components of the Williamson ether synthesis. And so you got to think here, going backwards. We're just breaking this bond back apart into the oxygen anion and the carbon with the leaving group. All right. How could we break this apart? Well, let's go backwards. And when we go backwards, we want to use this double line arrows called a retrosynthesis or retrosynthetic arrow. Going backwards. We can go back, but which oxygen-carbon bond do we want to break? Over here, obviously that's the one that was formed because we knew the starting materials. But we could have formed the other oxygen-carbon bond. Let's do that over here. If we form this bond, let's call that A, that would go back to that anion plus propane. Would these two react to give that? Oxygen? No. This anion is not going to react with propane. It has no reactivity. There's 3 H's here. There's only 2. We need a leaving group here. All right. How about a bromine? Would these two react to give that? Yes. These electrons attack here, kick that leaving group off, and that would give that product. This is coming forward. That's going backwards, our thought process, going backwards to what would be the, okay? It's like cooking. You want to make a what? 2-ingredient milkshake. We go back to ice cream and milk. Okay. But we could also go back another way. Now that was A. What if we formed that oxygen-carbon bond? B. Well, we would have the oxygen anion, the good nucleophile, and then we would have to have this part, but again, it needs a leaving group. So would these two react to give that molecule? Well, theoretically, yes. These electrons attack here, kick those off. That's an Sn2. That's an Sn2. So we can theoretically come up with or propose 2 different syntheses of this ether. But the question is, which one would be best? Which one would be highest yielding? The answer is the first one. And the reason is the leaving group is on primary carbon. Down here, the leaving group is on a secondary carbon. There's less crowding around the tetrahedral carbon that we're attacking. Okay? If you remember, sterics is very important with Sn2. We added that here, but we also stated that Sn2 largely affected by sterics, or significantly affected by sterics. So this would be the better synthesis to propose. Okay, try the next one on your own. We'll look at that in class. Okay, what about alkylation of sulfur? Sulfur is right below oxygen in the periodic table. Very similar. You take this thiophenol, okay? Thio means sulfur. It's a sulfur analog of a phenol. Hydroxide, all right? We're going to convert this to the anion. SH compounds are actually more acidic than OH compounds, if you remember from test 1, because the charge is going to be these electrons take the H, these stay behind. We're going to have the sulfur anion. That's a nitro group. We saw that with some resonance. In fact, this sulfur is resonance delocalized into the ring, but also into the nitro group. Okay, but it's still a good nucleophile. It's an anion. Sulfur tends to be a good anion because compared to oxygen, oxygen's more electronegative. It holds the electrons tighter, even though it's minus in those examples. Sulfur is not as good of a parent. These electrons attack and kick off the leaving group. Nitro, sulfur. The sulfur is now bonded to this CH2 group, and that's bonded to the carbonyl, and that's bonded to the phenyl. And we just made that bond there. I'm highlighting it for you just to clarify. Sulfur is now bonded to that carbon instead of the bromine. Used to be under my finger that carbon was bonded to a bromine. Now it's bonded to a sulfur. The remainder of what the sulfur is bonded to is still there. Nothing happened to that, of course. There we go. We just have a little bit more functionality here. We have this ketone and this nitro group. But from this point, this is your Sn2 backside attack substitution. What about nitrogen? Can we alkylate nitrogens? Okay. We are alkylating. The sulfur now has this alkyl group added, this saturated carbon. All right. Now with nitrogen, a neutral nitrogen is a good nucleophile, right? sp3, as long as it's sp3. And ammonia, it is sp3. The lone pair is in an sp3 hybrid. Now here I'm showing the nucleophile on the reaction arrow and the substrate with the leaving group sort of as the main starting material. Or in other cases, I showed the substrate with the leaving group on the arrow. It doesn't matter. They're both in the same flask. You got to recognize substrate with leaving group and potential nucleophile. These electrons, neutral nitrogen here is a good nucleophile. Attack, kick off the leaving group. And now the nitrogen is bonded to the carbon. And now the nitrogen's a positive charge though. The neutral became positive. And the nitrogen needs to lose an H to go neutral. All right. Now let's talk about this. Now the Br minus could theoretically take an H. Let's show these H's out here. All right. I'm not going to show any more writing here and to kind of mess this. But if the bromide took an H, left a lone pair behind, we would get the neutral product and we would make HBr. You can see that. The problem is this reaction is not going to take place because HBr is a strong acid. It has a pKa of about -5 or something like that. This has a pKa actually of about 10. And we see here that this is favored. This side is favored, thus the Br is not going to take the H and go to that side. It's actually going to come this way. It's going to stay here. In the end, Br minus will not take the H. This just sits here. If you want to take the H, you have to add a stronger base. And that's what I show here. Okay? Bases such as potassium carbonate or sodium carbonate, or any other base. All right? You can have something in judged in equilibrium. We'll see examples of this. Otherwise, again, this is just going to sit like this, and you would have the hydrobromide salt of the product here as your final product if you did not include a base. Now, there's actually a problem with this. This is direct alkylation. The problem is there is another base in the reaction. Potential problem. The ammonia could, once some of this is formed, it could come over here and take the H. And come this way. I'm not going to show full mechanism there. But that would put the lone pair back here and you would form ammonium bromide. That is possible. But what else is possible is this could then react again. And multiple steps here, okay? I'm not showing every single intermediate. You could end up with 2 alkyl groups on your nitrogen. Okay? And this could actually react again. So there's a lot involved here. In review, the initial product is your protonated amine, and the Br minus is not going to take it. It'll exist like this. We'll see addition of bases, but we also have to be aware that polyalkylation is possible. Some students who are aware of this would say, well, how can this act as a nucleophile? It doesn't have a lone pair. Well, the amine in the reaction can actually free it up and produce the lone pair, then it can react again. We'll refer back to this as we move forward. Now there's some alternative approaches to direct alkylation of nitrogens, and one of them is using sodium azide. This is just a good old Sn2 reaction. Charge of the azide, of course, is minus. This is Na plus, N3 minus. That's a minus. Azide looks like this. Each nitrogen on the end is minus, the one in the middle is positive. You see the net charge is minus, and thus it would have one sodium cation sitting with it. Either end can act as a nucleophile. This attacks here, kicks off the leaving group, and now you have N3 bonded to the carbon. That's condensed. At this point, you can hydrogenate this and cleave two of the nitrogens and produce the primary amine in good yield without polyalkylation. Now in Organic 2, we'll see other alternatives to direct alkylation. This would be considered an indirect alkylation. Okay, one other reaction we can show with amines. One other point is synthesis of quaternary amine salts, quats. If you take this tertiary amine, react it with the substrate with the leaving group. By the way, it looks like I'm using bromine as a leaving group a lot. That's because bromine is kind of the most common. It's a good leaving group. Iodide, of course, is the best, but sometimes iodine compounds are not fully stable. We could also use maybe a tosylate leaving group, but in this case, this will react here, kick off the leaving group. All right, Sn2, and the nitrogen is now bonded to an ethyl in addition to the two methyls and the other group, and we produced Br minus. And this is the end product. And this is called a quaternary amine salt, because the nitrogen is bonded to 4 alkyl groups. Now note that there's no H here, so it cannot go neutral by loss of an H. But these tend to be, or end products, and they tend to be useful. They're salts. And quats are used as antibacterial agents, and here's one here. Used in some hand sanitizers. I believe the ionic nature of the quaternary ammonium salt disrupts the bacteria the ionic nature. Also choline, which is you'll see in biochemistry, It's a precursor to acetylcholine or acetylcholine. Is actually a quat. The nitrogen has 4 alkyl groups and a positive charge. So you occasionally do see quaternary amine salts along the way. And here's actually another one. The world's most bitter compound is this salt. Of course, both the ions here are organic. It's a lot different from having a sodium ion and a chloride ion. Each of these being monoatomic ions. These 2 ions are both organic. World's most bitter compound. Okay, what about carbon? Can we alkylate a carbon? Well, typically carbon doesn't have a lone pair. Can we generate a lone pair? You can. One of the easiest ways to do it is from an alkyne. If you remember, the terminal CH of an alkyne has some acidity. This is where we ended with test 2 material. And do you remember what base we used to deprotonate terminal alkynes? One base we used was sodium amide, NaNH2. And the NH2 anion take this H, leave electrons behind, and we generate the acetylide anion. The sodium can sit with it, plus ammonia. Now we have a good nucleophile, a carbanion, lone pair anion. These electrons can now tack here. Do we have a leaving group? Tosylate. Kick off the tosylate. And we would get product here. Benzene, I'll just denote as phenyl. Triple bond. That carbon is now bonded to that carbon. And we have ethyl group and a deuterium. The carbon that the alkyne carbon is bonded to this carbon. This carbon has an ethyl and a deuterium attached. Okay? And we have stereochemistry here. Okay? Sn2. Sn2 comes with inversion. Just like Big Mac comes with fries. Okay, this comes in, it inverts, okay, remember transition state, all right. And so the carbon has another carbon added to it. We just alkylated, one carbon was alkylated with another carbon. We made a carbon-carbon bond in this case. Now, as one little side note about using this base, we generated ammonia. Ammonia is a decent nucleophile. It could have reacted here. that could give you a side product. The other base commonly used here is N-butyllithium. And if we had used this as base, if this had taken the H, we would have just made butane. And butane would not be a nucleophile, so it would not react here. No likelihood of it reacting here, no potential. But ammonia, which is generated when that takes an H, ammonia is actually a decent nucleophile. So that's one of the reasons why sodium ambid here, NaNH2, is not sort of the best choice of a base. But for some reason, textbooks love to use NaNH2 as the base to deprotonate terminal alkynes. Okay. Now we can also use cyanide anion. Cn minus. All right. It's triple bond. All right. But the carbon of cyanide is a carbanion and it can react. Kick off the leaving group. And I'll just make that phenyl. The leaving group is back, and so the cyano group would come forward. And let's just show that condensed. And Sn2 again comes with inversion. In the one above, the leaving group was in the plane to the right, and so the nucleophile is in the plane to the left. And the ethyl and the deuterium just move from one side to the other. All right. Now I showed both of those types of outcomes back during test 2. Remember the handout? This one here, leaving group back. Nucleophile forward. This one up here would be analogous to right here. Let's just turn it to the side. Leaving group in the plane to the right. Nucleophile now in the plane to the left. All right. The group forward is just, see the inversion, it's to the left, forward. It's hard to me to show forward on the video. Forward to the left, when this comes in, it moves over here, but it's still forward. Okay? It goes from forward left to forward right. Because we're looking over here. Now if we were standing over here, it'd be toward us and now it'd be going away. But we're not standing over there. When we look at our paper, we're standing up, we're standing here. And so we're seeing it come, it's towards my finger. But then when it moves over there, it's still towards my finger, but now it's on the right. And that's what I have here. Okay. Roman numeral I, a little bit different topic. Proving mechanism by product regiochemistry. Provide a mechanism for the following reaction. I actually want you to do this on your own. Think about things. First off, What type of nucleophile do we have? First off, are we doing leaving group chemistry? Yes, the substrate has a leaving group. Do we have a strong nucleophile? We have ethanol. That is a weak nucleophile. Can we do Sn2 here? And the answer is no. Sn2 requires strong nucleophile. What type of reaction was done here? It looks like the oxygen has replaced the bromine. The O-ethyl group has replaced the bromine. And it looks like a bromide maybe took an H or something to make HBr. But we also have somehow the nucleophile has bonded to another carbon. It looks like a rearranged product. Think about those things. But the hint is that perhaps this reaction is not Sn2, but maybe Sn1. Then I want you to repeat the reaction or predict the products if we included stereochemistry. Then answer the questions below. Now, I'll end this video by summing it up. What have we talked about? We talked about substrates with leaving groups on a primary carbon will only undergo Sn2 because primary carbocations are bad, right? Right there. Primary bad. That's why the original mechanism was not Sn1, Sn2. Substrates with leaving groups on tertiary carbons can only undergo Sn1. Remember we said that if the leaving groups on a tertiary carbon never do Sn2, right here, it's actually in bold. Never do Sn2 with a tertiary halide. Okay? And of course, it could be other leaving groups other than halides. Substrates with leaving group on secondary carbon can undergo either reaction. Yes. Now in this case, we will want to be looking for other information to help us to predict the mechanism, such as stereochemistry. Okay. Now we can also state that with strong nucleophiles, the reaction will always be bimolecular. Now for substitution, that's Sn2. With elimination, that's E2. Strong nucleophiles, always bimolecular. They're strong. They're going to stick their nose in there. They're going to be involved in the rate determining step. You can't keep them away. You can't keep them from reacting. Weak nucleophiles, on the other hand, which are lazy, will only react by a unimolecular mechanism. They're not strong enough to do Sn2 or E2. Unimolecular is Sn1, or we'll see as E1. But as long as the substrate is secondary or tertiary, Because of course you don't do Sn1 with primary halide, or when the leaving group is on a primary carbon. Thus, if the substrate is primary, the reaction will have to be bimolecular. Of course, a bimolecular reaction with a weak nucleophile will be quite difficult, and it may not occur. Okay, most of the stuff you sort of already know from what we presented earlier. But this does sort of sum it up for us. We'll refer back to this as we move ahead, and as you start working problems. Some here to work. Again, I've posted the answers to these, but of course please work them before looking at the answers. You also have on the first page of mechanisms, and on the back there was a second page back here. Please take a look at this. I hope to maybe look at this in class. It's important. Questions here. There are 3 examples of Sn2 reactions on this page where it shows a synthesis of the antihistamine drug Zyrtec, which some of you maybe have taken before. Okay guys, so that finishes up this handout, but there's a lot here. Keep working at it. See what type of questions come up. Then we'll be moving on to elimination reactions.